So next let's talk about how we're going to, let's derive the estimators that we're going to use for beta 0 and beta 1. So those are those beta 0 and beta 1. So let's just write it down. Deriving OLS estimators. It's easier if we can maybe visually see what we're trying to do. So y equals beta 0 plus beta 1 x1 plus u. And if you remember, we said that these two things were parameters. So if you remember from the review of stats last module, we're coming up with estimators that take our sample, apply some rule, and give us a value for these parameters. And we wanted certain properties of those estimators. So that's what we're talking about doing now. How do we come up with estimators for beta 0 and beta 1? What are our estimators? What are our rules that we use for any given sample? Okay. So let's, to do this, we need a sample and an estimator. And an estimator. So like some kind of rule. So we talked about 3 different kind of approaches to estimation. So we need kind of one of these approaches that we're going to kind of implement to get estimators for these parameters. So let's first think about writing out our regression this way. So notice I added this subscript I. So it's like the observation subscript. Observation subscript. I think I need to change this pen. Hopefully it still comes through. Observation subscript. So each person in our sample, remember there's n people in our sample. This is the ith person's value for y. So if I equals 3, then this value, so y subscript 3 is the third person's, let's say, wages or something like that. So notice that with both of our variables, y and x, there's an I subscript. And every person in our sample is going to have some level of u. I mean, we don't get to see u, it's unobserved, but some level of u. Everyone has their own. Okay, so let's kind of think about our least squared approach to coming up with an estimator, and we can derive the estimators for beta 0 and beta 1 here. All right, so we have our regression function here with these 1i. Sometimes I forget the 1, but we're only kind of dealing with 1x right now. So just assume there's kind of a 1 attached to this x if I forget. Just like in class. All right, so let's rearrange this just a little bit. So think about ui being the difference, the error term here being the difference between, let's try to erase that with my finger. Oops, and this should obviously be a minus if we don't have it in brackets. So this error term is the difference between these observed values, and then kind of we're subtracting what our beta 0 and our beta 1 times x1i. And so what our estimators kind of try to do is minimize the sum over our entire sample of kind of the distance, how far off we are in terms of the actual observed value and kind of what our model is predicting for that level of x in terms of the value of y. So that's like the idea here. Trying to minimize, so we're squaring it, so every value is positive, so we don't have negative and positives cancel out. Another way of doing that is with absolute values, right? But maybe those derivatives are a little too hard for us. So we want to minimize this squared distance between our kind of observed values of y and what our kind of, think about as like predicted values of y is going to be. So that's kind of what we're thinking about. So let's exactly plug in you could hear the pen drop maybe, plug in ui equals yi minus beta 0 minus beta 1 x1i. Just from here, right? I mean, that's essentially, I'm just rewriting that. Okay, so let's plug that in. Now where'd my other pen go? My blue pen? Over here. Okay, so we're gonna minimize the sum over our, from I equals 1 to n, so this is our whole sample here, our sample size is n, yi minus beta 0 minus beta 1 x1i squared. We're just plugging that in there. And so this is what we're trying, like this is our least squared estimator. Now, we're minimizing, but we got to minimize over something. Well, what do we get to pick? We get to pick what our estimators are, right? We get to pick beta 0 and beta 1. So maybe this is our estimator here. Our estimator is W, and it's whatever beta 0 and beta 1 we get that minimize this square difference between our observed values and kind of what our guess is or our estimate is. So that's the idea. Well, you might have seen minimization and maximization problems in like intermediate, micro, or macro. Well, when in doubt, we take the derivative, right? So we have two derivatives to take here, one with respect to each of them. Let's use a different color. Maybe I have one. Okay, so let's take the derivative with respect to beta 0 and then the derivative with respect to beta 1. So we're trying to minimize this, so we're going to take the derivative and we're going to set it equal to 0. So let's take the derivative of this function with respect to beta 0. So the derivative of the inside is minus 1. Right? And then we need the derivative of the outside. Well, this comes down and we have everything still, right? So minus 1 times, oops, we don't need another minus there, 2 times the sum yi minus beta 0 minus beta 1 x1i. And we know that equals 0 at its minimum. Derivative of the inside, derivative of the outside. Chain rule, right? The only thing that might be kind of confusing is those sums, but you'll get used to them. Okay, now we can take the derivative with respect to beta 1. So again, we have a minus there, so it's minus 1. But we have this x1i still attached. So again, we're going to have this minus 1. But then we have the sum. Ooh, that was a bad one. Should put I equals 1 to n here too. The sum. Again, now we have that extra x1i here. It looks a bit different than the one above because we have this x1i attached. So this is the derivative kind of the inside. We're halfway down the whole thing now. Derivative of the inside. And then derivative of the outside, which is the same as before. So again, we can just put a little 2 there. That's that exponent coming down. And then we have that this whole term again here. Oops, minus beta 1 x1i equals 0. Well, pretty easily we hopefully realize we can just get rid of these front two, all the constants kind of outside of the sum, because we can just divide both sides by -2, right? And we get rid of those. So now we have two equations here. And two unknowns. with beta 0 and beta 1. Now I'm going to go back and do something really quickly. This is going to be somewhat, I mean, it's important to understand kind of what's happening. So these beta zeros, remember, were the true values. But now we're coming up with an estimator. They're not representing the true values anymore. So as soon as we take the derivative, we should start putting hats on these betas. And the hats are kind of indicating that they're estimates or estimators, right? Without a hat, it's like the true value. So whenever you don't see a hat on a beta, it means it's the true value. These are not the true values. These are what we're coming up with as our kind of guess, I mean, educated guess through statistics, of what these values are. So that's why there's these hats on them here. Okay, so we have two equations and two unknowns. So let's look at that first one. So after we canceled out that -2, we had the sum of yi minus beta 0 minus beta 1 x1i bracket, and I should remember what we just talked about, put the hats on it, and that equals 0, right? Because we're minimizing something, so we're at the bottom of that, of the function. Okay, so what we're going to try to do here is we want to isolate beta 0. So we're going to get beta 0 in terms of y and in terms of x1. And beta 1, I guess, right? Okay, so that's what we're trying to do here. So the first thing here is we can start to think about separating these sums. So now let's kind of separate some of these sums. Minus the sum of beta 0 hat, and we should talk about that in a second. Minus, now notice that, again, beta 0 and beta 1s, there's no subscript I on them, right? They don't change with each observation. We're having one parameter estimate in terms of the return on education for everybody in our sample. That's what we're trying to do. So there's no I subscript, so it's a constant. So we can kind of take it out of the sum. We can do something else with that beta 0 we got to talk about in a second, I guess, equals 0. So we just kind of took that sum through. And again, all these sums are 1 to n. I just get lazy. Okay, so the idea there is that beta hat 0 and beta hat 1 are constants. Okay, and then we should talk about this second, let's simplify this second term now too. So we have the sum from I equals 1 to n. Again, I'm going to stop doing the 1 to n part, but 1. And now we're subtracting beta 0 hat n times, because it's from 1 to n. So n times beta hat 0. Let's just rewrite the other. Equals 0. So this again, just using that same thing, this idea of beta 0 being a constant. All right, then we're going to start to isolate beta 0. So we're going to either think about moving this to the other side, but I'm going to kind of leave it over here. So n times beta hat 0 equals the sum of yi, I don't know why it says y1, yi equals 1 to n minus beta hat 1, the sum from 1 to n, x1i. So we're just rearranging that. All right, so now what we can do is move this over there by dividing, both sides by 1 over n. I don't know if we're moving it or, we're dividing both sides by n to get rid of it. So then we're stuck with, or not stuck with, but then we get beta 0 is 1 over n times the sum of yi minus beta hat 1 times 1 over n times the sum of x1i. And notice that this is the definition of the average value, or the sample average of y, and that's the definition of the sample value of x. So we end up getting beta hat 0 equals y bar minus beta hat 1 times x bar. I guess 1 should be the subscript. And so that's what our estimator for beta hat 0 is. Y bar minus beta hat 1 times the sample average of x. X1, I guess. So we're going to have to solve for the other one now, right? We're going to have to take this and plug this in to that other first derivative that we took before. And once we solve that, we're going to get an estimator for beta hat 1. Beta hat 0, this is our estimator. Now we're going to plug that in to get a rule or an estimator for beta hat 1.